Alright, you're going to get something that you don't get that often from me here. You're going to get some slides. And we're going to, and this really is just down to my penmanship. If we were in a classroom with a blackboard, I would do this on the board. The type of tablet I'm using here right now, I've redone my setup a little bit, and my penmanship's better than it was beginning of the semester. Works great for numbers, but for some of the drawings I'm going to have to do here, I'm going to use the slides. So I do apologize for that. I know you can read the slides, so I'm going to try to highlight some things and go from there. And so we're going to look at graphs while I'm doing it and what it means to have areas under a normal curve. And so what we're doing is we're looking at continuous random variables. So we're moving from discrete random variables to continuous random variables. And the thing to note is that there is an infinite amount of values that we can get in here. Right? I can get 6.13, 6.128, 6.0, right? When I pick from here, these values are smeared. We tend to say real numbers are infinitely dense and they can fill their space. And it's odd and hard for some people to get used to sometimes when we think about numbers, but they have definite endpoints. Right? This is a closed space with a definite endpoint. You can have 0 and you can have 24 or any possible value in between. Unlike our discretes, which were only at given points. And so a continuous probability distribution is one that uses random variables. And we're going to have to look at these. The distribution we're going to use or begin with is the normal probability distribution, the normal distribution. It's also called a Gaussian, because Gauss wrote the function that describes this shape, or a bell curve. And I'm just going to caution that the word normal here is not the same as normal in the English language. We use normal in the English language differently than what a normal curve is. Though some of these ideas will overlap, the normal curve shows where most things are lined up. And in the English language, we have this idea that normal is where most things are. But there's kind of a restrictive way we use it in the English language, or almost a detrimental way. While in mathematics and the observation of statistics, we're looking to see where most things are. And as with anything, it's the questions we ask that determine what our answers are. The book says this, and I'll say this, and this is probably the most important distribution. The things we learn in chapter 5 will come up over and over and over and over again. The normal distribution arises very naturally from some concepts. And what we have here is this is what it looks like. And we noticed it in chapter 2. Whoops. Let's see if I can get my dots on here, okay? Oops, it's drawing lines. That's 1 standard deviation, and that's -1 standard deviation. Whoops, come back. And it's clicking on me here. What is it doing? And that's the mean. Now, this is a symmetric distribution. There's the same amount on either side of the middle, and the middle is the mean. Well, if there's the same amount on either side, that means that, whoops, that the mean is also the median. For some reason this wants to do lines. Well, we'll bring it over here. And so in this case, the mean, the median, and the mode are equal. I will say the mean more often than not, even though I might be talking about it as if it's the median or the mode. And we can look at it if we think about each possible measurement we make being a dot that fills up the space here. And we get an area that the total area under the curve is 1. Just like our discrete probability distributions where the rectangles added up to a total area of 1, we're going to use this mentality that the total area under the curve is 1. And so any area will represent a probability. But notice that this line here, I can stack up the most dots, and hence that's why it's also the mode. It approaches but never touches the x-axis, and this actually goes off to positive infinity and streams down to negative infinity. Though we will find that we can talk about certain values as being close enough to zero that the curve ends or begins there. But the real Gaussian distribution flies off towards infinity or negative infinity, and you never quite have all of it within a finite distribution. But that's okay. We'll see that you get so close to x that we can say it's good enough to be zero. Notice that the thing we're going to need to find probabilities are we're going to need areas. We're going to talk about the area between two values. And so we'll talk about our probabilities will have to smear. Just like we say continuous variables smear, our probabilities will have to be between 2 points into a smear so that we can add up that area. We can add up that area and figure out how much of the total area it is. When we talked about this distribution and we observed it in chapter 2, we mentioned the inflection points. And the inflection points are above the inflection points, this is curved downwards. After the inflection points, it's curved upwards. And that talks about how the function is changing. This function is getting smaller quickly, and then it gets smaller more slowly. But those inflection points happen one standard deviation away from the mean. And so we have the mean plus 1 standard deviation and the mean minus 1 standard deviation. Remember, we had the empirical rule that said there was 68% of the stuff here, and we had 95% of the stuff between 2, and we had 99.7. We're going to look on how we can get those percentages and how we can manipulate those percentages. Alright, and so that's our introduction to the normal distribution as its own. I'm going to continue looking at the probability density functions in a little more detail in the next video.